Welcome to Radio Systems Design, Module 8, Advanced Transmitter Architectures. In this module, instead of talking about hardware designs of transmitters, we're going to talk about a little bit more about the system design of transmitters and some of the standards that are out there. This will make you aware of how most of our modern digital transmitters work from a system perspective, and from the basic building blocks we've learned in the previous several modules, you should be able to see a link between the two. In this module, we're going to cover duplex communication, multiple access, and multiplexing. And all the concepts are actually pretty straightforward. The one thing you just want to keep in mind in your head is that try to think as we go along what the term duplexing means, multiple access, and multiplexing, because each one does time and frequency domain aspects. And as long as you keep straight what's duplex, what's multiple access, and what's multiplexing, everything should be pretty straightforward. All right, duplex communication. In a simplex communication, one device transmits and the other just listens. So an AM radio is an example of a simplex communication system, or a pager or remote control where you just have one transmitter and the receiver is basically, in one sense, dumb. It does not transmit back to you. A duplex system, as the name would imply, involves a two-way communication between two devices, so both transmission and reception. And that you can have full duplex where both talk back and forth, and half duplex where maybe one can only partially do communication. So in time division duplexing, we're going to send and receive at different times. So the basic idea is, let's assume we have here the transmitter and here the receiver. At a certain time, the transmitter will turn the switch to transmit and the receiver will close the switch to receive. And then once this is done, when the receiver wants to reply, it will simply close the switch to transmit, and the transmitter will close its switch to receive. A simple way to think about this is in a walkie-talkie, you push the button to transmit, you let it go to receive, and you coordinate sort of implicitly with the other person so that you can talk to one another. Some points here to notice: that both the transmit and the receive operate at the same frequency. Time allocations are not necessarily equal. Just as an example of a walkie-talkie, you can talk as long as you want and the other one can listen as long as you want, so there's no pre-existing coordination of time. And it allows peer-to-peer communication, as an example with the walkie-talkie. Frequency division duplexing is when you send and receive at different frequencies, and this can actually be performed at the same time, which would be the benefit. And as you can see here in the diagram, the transmit frequency and the receive frequency are different. So I can actually transmit data and receive data from the transmitter to the receiver simultaneously. And so obviously this has a benefit of we don't need to coordinate times, and we can have transmission of data happening simultaneously. One of the challenges is separating the two frequencies and building these filters that separate the two channels. And the reason is typically you're operating in a certain allowed band by the FCC, and so if you're operating at two different frequencies, both of those and the spectrum around each needs to be within that band. And base stations in the case of cell phones translates the T and the RX bands. And the other downside of this is that two pairs of transmitters and receivers are needed in a point-to-point communication. As you can see, I need two sets of hardware here, two sets of hardware here. And while we haven't covered receivers except a little bit in analog modulation, you probably already have a feeling for receiver architecture is going to have a lot of the same components as a transmitter architecture. So that if we were able to reuse portions, that would be helpful. Or we may be able to at least have them co-located, whereas in frequency division multiplexing, this entire circuit is operating in an entirely different band than that circuit is, so you couldn't necessarily reuse LOs as an example. Now we're going to move to this concept of multiple access. Duplex was about two systems communicating with one another. Multiple access is about multiple people communicating on the same network. And it's used in point to multi-point communication systems. And a great example is in the mobile network, our cell phone industry. So we've got mobile phone users within a single cell area communicating with the base station. And you can see here these towers, and they're all trying to talk to all of these phones here. So in multiple access, there's a few different standards. One is frequency division multiple access, and you probably already have a good idea how this works. Each user is given a frequency and can only transmit frequency on that communication, on that frequency. At the end of the communication, the channel becomes available to other users, and the channel information is sent to the user before the actual communication. So we would actually tell the cell phone, please use this frequency for your next communication, and it would be dedicated to them. They transmit on that frequency, and when they're done, it would be released, and another cell phone could be told it could use that channel. Another standard is sort of the dual is time division multiple access, TDMA. And each user is given a time slot in which it can communicate, and the communication happens in bursts. So in this case, we would coordinate between the base station and the mobile phones and basically assign each one a different time slot, as you can see right here. Now, part of the challenge here is this actually involves quite a bit of coordination of time, and that puts a little bit of a burden for overhead in getting each cell phone or each radio to talk at the appropriate time. However, there's enough bandwidth out there that this is easily done. The cell phone is still on, and it's still working between bursts, but basically it does its transmission and then it goes into a quiet mode where it's just listening for information, in particular overhead about when its next time slot would be. In many systems, we can actually combine both time division and frequency division multiple access. And on the bottom here is a nice diagram that shows how we do that. We basically can split our total channel bandwidth up into a set of frequency channels, and then we just do time division multiplexing as we move along in time. And so this means that each frequency channel is shared between multiple users, and there's multiple frequency channels that are being used at the same time. So as you can see pointed out here, users are each one of these little blocks in here. And finally, I want to talk about code division multiple access, or CDMA. And if you're not aware, this is the big patent that Qualcomm has, and I believe it's with Etri in Japan helped develop this. This is a patented technique that's given them really most of their intellectual property to start out with, and has been a key patent and IP in the cell phone industry. And the concept of CDMA is that all the users are sending and receive data at the same time and at the same frequency, but it's in code. And so people can talk to one another. And it's sort of like an example would be if people were talking in different languages. If you were in a room with other people and you spoke English and French and someone was speaking French, you could understand them, but if somebody was speaking German, you would probably just ignore them. And so in time and in frequency, we're basically stacking all of the users on top of one another. And I'll show you next how exactly they're able to do this and what we mean by a code. These codes are combinations of ones and zeros, and a Walsh code is a common type of code that is used, and they call these codes chips. And the chip duration is usually much smaller than a symbol period. You can go out there and Google Walsh codes and chips if you want to learn more, but the basic idea is there's a specific coding that we're using to code up each one of these. And down here in the bottom, I've kind of showed you the cartoon of here's what we'd like to transmit for user 1 and user 2, and we're going to multiply it by a code. And each phone is going to get a separate code. And that code is going to expand the bandwidth of the signal that we want to transmit. And so these are sometimes called spread spectrum because they have a wider bandwidth than the original signal. And the receiver is going to decode by basically applying the same code. So to use the analogy before, the person who speaks French in the room will be able to decode all of the French messages being sent. Here it's actually a digital code. And by having a unique code, it basically can listen into only the part that it wants to. The coding and decoding is all performed in the digital domain, so probably you immediately can see why this is a benefit, because all of the complex math that's needed is done digitally, which we have high-end microprocessors for. And the radio part, the front end, which would be the transmitter and the receiver, have less of a burden because to them they're just transmitting a wider bandwidth signal. One caveat here is that the receiver would like to receive all the signals at the same power. Obviously, they're not when they hit the antenna, and so what the receiver does is basically normalize the power internally before it applies the codes. And finally, let's talk about the idea of multiplexing. Multiplexing is when we're taking several pieces of data and we're going to put them into a single stream. So it's a little bit different than multiple access. Multiple access is about phones talking to one station at a time. Multiplexing is about taking that information once it's received and sending it through a single transmit mechanism. So an example would be if the base station collected all the cell phones. In this example, the mobile network, we'd have a little cell phone here, would go to the base station. The base stations would send all their information into an aggregate point. They aggregate into another, and then it might go out on fiber. And the question is, how do we put all of the information together on that single fiber channel? And so here's a picture of what a tower looks like. Here's a great example of an aggregating tower. You've probably seen these around. And so we'll first talk about time division multiplexing. And you can see here on the diagram that you basically have a number of inputs. And in time division multiplexing, we're just going to take a switch and connect it at different times to each one. And then we're going to have in the time, we're going to have interleaved each of the inputs. And then the receiver would just do the opposite. So TDM is a technique to combine several data streams. And as I mentioned, it's placed in different time slots. This works really well when the speed of this information coming in is slow compared to the rate here. And just to give you an example, optical fiber can run at 40 gigabits per second. Okay, and your average cell phone is probably maybe operating at a few megabits per second. So you can see you can fit quite a few of those into a transmit frame here. And the dual of this is frequency division multiplexing, as you might expect. What we do is we just put each input into a spectrum, and then we can transmit all of this at once. And the benefits of this is that if your transmit channel is not very fast, meaning I can't get much more data through it, but I have a wider bandwidth, this is an option to do this. In this, in example of fiber optic cable, they actually do this where they'll put different light streams. So if I have different lights shining through my cable, I can actually put on each one of the different wavelengths of light a series of communication and get higher communication. Just one little side note on fiber optic. The one thing that it's just starting to happen, but it's not really mainstream, is that in the past, fiber optic has been a binary on-off key. So you get a 1, a 0, 1, a 0, 1, a 0. And the reason they did that is they can basically translate, like I said, 40 gigabits or 100 gigabits over optical fiber because the transmission loss is so low. It's very difficult to build the electronics that can do 40 and 100 gigabits, but the basic idea of the fiber is it's open to almost unlimited bandwidth, or I'll say relatively unlimited bandwidth. So there hasn't been the necessary to do complicated things like amplitude and phase modulation. In addition, because you can transmit at different colors, different wavelengths, you can actually stack a bunch of high-speed on-off key communication standards right on top of one another. So fiber up until recently and even now still is really not a bottleneck. We can pretty much put as much data as we need across it. And if we need more, we can just start to do what radios have done for the past 50 years, and that's start to adopt more advanced transmitter architectures such as QAM and PSK that we've studied before. And here's an example that in the old analog telephone system, frequency division multiplexing was something that could be done. All right. In this module, we've covered 3 different types of communication systems: duplex, multiple access, and multiplexing. And in each one of them, we've basically had a time domain and a frequency domain version of each. And the only exception here was under multiple access, it should be a C, CDMA, was a invention by Qualcomm, and I believe Etri in Korea participated in that, and created a way to basically code up our messages, and that allows them to use the spectrum more efficiently and get a higher communication throughput than other standards.